Consider this scenario. In a room with a floor that measures 4 by 5 meters, what is the total force on the floor due to the air above the surface if the air pressure is at 1 atmosphere? Well, let's draw a little sketch. We have a home. Here is a home. Just your standard house. Has an attic and a second floor. Here's the second floor. And it has a first floor and a front door. You enter into the first floor. And let's put this particular floor right here, excuse me, on the second floor, up here. And we'll divide the top here in a couple of rooms. But this is the one that we're interested in, this floor. And this floor right here on the second floor has some dimensions, 4 by 5. So we'll call this 4 meters in depth by 5 meters wide. And it asks us what is the total force on this floor as a consequence of all the air that is pushing down on this floor. So there's air pushing down on this floor. We need a little bit of background information first. We live on this planet called Earth. Now I'll just draw Earth here. Here's where we are on Earth. And Earth is surrounded by an atmosphere. And this atmosphere we call air. But air is also a fluid. So we actually live in a fluid called air. We live in a fluid which we call air. And the fluid, this air that surrounds our planet, it is open all the way into space. And our house is situated here, at the bottom right here, on the Earth's surface. And all of the weight of all of the air from here all the way into space is pushing down on the house, on the floor, and on the surface of the Earth. And this has been measured, and it has known as 1 atmosphere. The pressure here at the surface is known as 1 atmosphere, written as 1 atmosphere. It's also known as, in the metric system, the pressure here is 1.013 times 10 to the power of 5 pascals. So we live under pressure, and this is the pressure that we live under here because of all of the air that is above us, all the way into space. Having had this little bit of background information, if we look back here, we're asked to find the pressure of the air on this surface, right here, this floor. And that air is from here all the way into space. The roof that's above, it has no impact on what it is that we need to calculate. Just from here all the way to space. Let's have a look at our equations. Equation we're interested in is this one. Pressure is equal to force divided by area. And we also need to understand here the pressure of 1 atmosphere. This is the pressure of all of the air pushing down on us from the surface of the Earth that extends all the way to space. We live in 1 atmosphere, and it has the value of 1.013 times 10 to the 5 pascals. Or in other units, it's also known as 760 millimeters of mercury. This is also 1 atmosphere. Or sometimes it's called 14.7 pounds per square inch. And again, this is all equal to 1 atmosphere. And all of this relates to the pressure from all of the air above us at the surface level. Or at sea level, all known as 1 atmosphere. And we're interested in this value here for our purposes. You can easily do the conversions. This is, in fact, a conversion table. Having said that, let's have a look at our equation. Pressure. Pressure is equal to the force divided by area. And when I write pressure, in order to distinguish it from density, density is rho. This is rho. I put a little stem here at the top of the letter P. This is the letter P. And I put a little stem up there. I want to distinguish it from rho. So when you look at this video, you'll notice that this is pressure. I'm not talking about density. So pressure is equal to force divided by area. Let's have a look at the units. Pressure is equal to, looking at the units for force, and all force has a unit of a Newton. And area, we want to know the area of this floor. And in base units, that's done in meters. So meters times meters is square meters. Meters squared. So pressure has the units of newtons per square meter. But this combination has been given a special name, a Pascal or a Pascal. And that's abbreviated to PA. And this is in honor of Blaise Pascal. Here he is, Blaise Pascal. Little comment here. 1647. He proves that air pressure decreases at higher altitudes. So the unit of pressure is named after Blaise Pascal. And I simply pronounce it a Pascal. Anglicize it here for our purposes. So pressure has the units of a Pascal, or Newton per square meter. And here's the equation. And now let's have a look at our word problem itself. In a room with a floor that measures 4 by 5, what is the total force on the floor due to all the air above the surface if the pressure is 1 atmosphere? So we know what the pressure is. 1 atmosphere, or 1.013 times 10 to the power of 5 pascals. The area that we are interested in is this one, which is 4 by 5, or 20 square meters. So area, 4 meters by 5 meters equal to 20 square meters. And we're asked to find the total force, which is this value. So we have everything we need, just a matter of putting in the numbers. I'll do that over here. The pressure in pascals, 1.013 times 10 to the power of 5 pascals, or Newton per square meter, is equal to the force, and force has a unit of a Newton, divided by the area which we are interested in, which is this whole area, 20 square meters. Rearranging this in order to isolate force, multiply this side by 20. Whatever we do to the right, we have to do to the left, so we multiply that by 20. 20 square meters, of course. This will cancel out, leaving us with 20 meters squared times 1.013 times 10 to the power of 5. And a Pascal is a Newton per square meter. And if I write it in this form, they're one and the same, is equal to force. But in this form, I can cancel out square meters, leaving me with force, and all forces have the unit of a Newton. Doing this multiplication, the answer is 123, and has the units of a Newton. 2 million newtons. Rounding this number here to two significant figures. Approximately we're going to go 2.0 times 10 to the power, decimal point is here, 1, 2, 3, 4, 5, 6. So the force acting on this floor, as a result of all of the air from here all the way into space, is 2 million newtons. Now, what's 2 million newtons? I don't know. I understand pounds, but we can convert this to pounds. Doing that conversion, 2026 newtons times 0.2248 pounds per 1 Newton. And that's equal to, the newtons will cancel out, 455,445 pounds. Oh my God. 455,000 pounds is resting on top of that floor. That is a huge number. We can change this into tons simply by dividing by 2,000. Divide this by 2,000, okay, pounds per ton. That gives us approximately 227 tons. That is the weight that of all the air that is being applied on this floor. And the question now comes, oh my God, that is a huge, huge number. There is no way that this floor has been designed to withstand a weight of 227 tons. So why doesn't it collapse? Remember what I said here earlier? We live in this fluid called air. And air is everywhere. It's all around us. And because it's a fluid, being a fluid, it will exert pressures in all directions. Here at the Earth, at the surface of the Earth, the pressure being exerted in all directions is 1 atmosphere. So if we were to look at this, the force being pushed down, if you look at it in terms of newtons or pascals, 2 million newtons is all the force being pushed onto the floor. But there's also air underneath. And that air is also pushing up with the same force. So the force going down, force downward, is equal to the force of all the air underneath it pushing up. As a result, the floor itself feels zero. The net force on that floor with the air pushing up and then the air pushing down above it equals 0. Hence, the floor doesn't fall. And it comes back to this, where we live in this fluid called air, and this air is, well, everywhere. It's in this room, it's in here, it's in the attic, it's down here, and if we had a basement into the ground, and the ground here is open to the atmosphere, it will be down here as well. And this pressure, the atmospheric pressure, is exerting a pressure in all directions, on all the floors. And even though this is a huge number, and it's true, it is a big number, it cancels out because of the vectors going up is equal to the same vectors coming back, pushing back down. Net force then is 0.